In this video, we are going to discuss about what is Archimedes principle. Suppose a body is fully or partially immersed in liquid. Suppose a body is fully or partially immersed in liquid. See, I'll draw the figure. This is a container, and we have liquid in this container. We have the liquid in this container. And suppose we have a body which is immersed in this liquid. Suppose we have a body which is immersed in this liquid. Suppose this body is immersed in a liquid, right? And suppose the volume of this body, or say mass of this body, is m. Alright, now this body is going to interact with all the fluids in the surrounding. So all the fluid in the surrounding is going to exert a force on this body. All the fluid in the surrounding, they are going to exert force on this body. At any point, the force will be equal to pressure into area. If I want to calculate force on, say, this small area on this body, then force on this small area is going to be pressure over here into area of this. If I take any area ds, then force acting on this ds would be equal to pressure at that point into ds. That will be force acting on the body. So this body will be subjected to force from all the side. This body will be subjected to force from all the side, right? And resultant of all these forces, Archimedes said that resultant of all these forces acting from all side will be in upward direction. Resultant of all these forces acting on the body will be in upward direction, and that's called buoyant force, and that is equal to weight of the liquid displaced by the body. That is rho of the liquid, rho L, into volume of this body. Rho L into volume of this body would be the mass, and into G. Rho L is the density of the liquid, V is this volume V, and G is the acceleration due to gravity. So this is the buoyant force which will be acting on the body, and that will be acting in upward direction. So a buoyant force, when a body is fully or partially immersed in the body, then a buoyant force acts on the body, and buoyant force is equal to weight of the liquid displaced by the body, and it acts in vertically upward direction. It's act in vertically upward direction. This is the buoyant force. This is the buoyant force which acts on the body, and we can prove this fact. We can prove this fact. You want to prove that the net force exerted by the fluid in the surrounding on this body is equal to rho L into V into G, where rho L is the density of the liquid, or force, buoyant force acting on the body is equal to the weight of the liquid displaced by this body, right? And that is acting in upward direction. We can prove it. See, in order to prove this, that buoyant force is equal to weight of the liquid displaced, let's do one thing. Let us replace this volume. Let us replace this body by same liquid. In order to prove this, that the net force acting on this body from the surrounding fluid is equal to rho L Vg, that is equal to weight of this liquid displaced by this body in the liquid. So in order to prove this fact, that buoyant force is equal to weight of liquid displaced, we have to prove this fact, right? So let's do one thing. Let's replace this body with the same liquid. Let's consider that you have a liquid, a volume of liquid having same shape, everything is same, we construct a sample of liquid, same liquid as you have in the surrounding. Let's consider a sample of liquid. Suppose that body is replaced by a sample of same liquid which is having same shape and size and same volume, everything same, but we are replacing the body by the equivalent sample of same size, same volume, same dimension. So we are replacing this with sample of same liquid as you have outside. So since this is same liquid and this is also same liquid, so the whole thing becomes homogeneous, and then this sample of liquid will be in equilibrium. Since this liquid is same, so it's homogeneous medium, as if there is nothing else, nothing over here. So this sample of liquid will be in equilibrium. And what are the forces acting on this sample? What are the forces acting on this sample of liquid by which you have replaced this this body of mass m? On this sample, the forces acting will be how much? One force will be weight of the sample, mg, and m is the mass of this liquid. And since this is in equilibrium, you must have, see, this sample of liquid is subjected to force from outside also. So net of resultant of these forces must lie in upward direction. Only that this sample of liquid can remain in equilibrium. Since this sample is experiencing force mg from the earth, and this sample is also interacting with the external fluid. This sample is also interacting with the surrounding fluid. So resultant force of interaction which it has with the surrounding fluid, that resultant must point in upward direction. Why? Because only then this F and mg will balance and this liquid will remain in equilibrium. So this force F is equal to mg in vertically upward direction. So resultant of all these forces is F in upward direction, that is equal to weight of the liquid displaced, weight of the liquid which is lying in this volume. So if I replace the same liquid by again the body, if I replace the liquid sample with the body which we had earlier, then also this dimension of this body and dimension of this liquid sample is same, and this forces also remain same. So I can say resultant of these forces is again F, and which is equal to mass of the liquid, which is equal to weight of the liquid which can reside in this region. See, this force is not changing. If I replace this liquid sample by the body of certain mass m, then these forces are not changing. And resultant of this force will be mg in vertically upward direction. What is this mg? Mg is the weight of the liquid which would reside in this region occupied by this body of mass m, weight of the liquid which is lying in the region occupied by this body of mass m. So on this body also, the resultant of these forces which is acting from the surrounding fluid will be in upward direction, and that will be equal to weight of the liquid displaced by the body, and this is called buoyant force. Right? This is called buoyant force. So buoyant force acting on the body. See, and one more thing, we have done this analysis from the point of view of inertial observer, right? We have taken an observer outside who is seeing this liquid to be in equilibrium. So in inertial frame, the buoyant force would be equal to weight of the liquid which is displaced by the body, and that is equal to this. That's called buoyant force, and that the whole phenomena is called buoyancy. So if you emerge any from this Archimedes principle, we have the principle of what we call principle of flotation, right? Principle of flotation, which says if this buoyant force acting on the body is equal to the weight of the body, then the body will float. If buoyant force is equal to weight, the body is going to float on the liquid. That's the called flotation. Suppose we have the liquid over here, and suppose we have a substance, say like this, and suppose rho L is the density of the liquid and this is rho of the substance. If rho is less than rho L, if rho is less than rho L, then the whole body, in order to float, the whole body need not immerse in the liquid. Only a part of the body can emerge, and that will be enough for the body to float. See, the mass, what is the volume of this body? Volume of this body would be m by rho. Volume of this body is m by rho, right? M by rho. And in order to balance, if rho is less than rho L, in order to balance this weight, in order to balance the weight, the buoyant force, how much buoyant force is needed? The buoyant force we need is F equals to mg, where m is the mass of this body. M is the mass of this body. So in order to generate this buoyant force will be equal to rho L into volume of water displaced into G equals to mg, right? And volume of water which need to be displaced will be equal to what? Suppose this is V dash. Suppose V dash is the volume of water which has to be displaced in order that this buoyant force equals to mg. So volume of water which need to be displaced is equal to mg upon rho Lg, and mass is how much? Rho into V upon rho L, and rho is less than rho L. Rho is less than rho L. So this is, and this quantity is more than 1. So the volume of water which need to be displaced is less than the volume of this solid. If the density of this solid is less than density of this water, density of this liquid, then volume of water which need to be displaced so that the buoyant force acting on this body is equal to the weight of this body, that volume of water which should be displaced is less than the volume of this solid. So only a part of the body will emerge. Only a part of the body will emerge, and that will be enough to balance the weight of this. That will be enough to balance the weight of this body. Are you getting a point? See, we have this body of mass m, right? So in order to balance the weight, in order that body should float, the buoyant force must be equal to the weight of the body, and buoyant force is equal to what? Weight of the water displaced. Suppose the water which need to be displaced is V dash. So from here we are calculating V dash. V dash is mg upon rho L into G. G cancel out. Mass is what? Mass is rho of this body into volume of this body, right? So this can be done as V upon rho L by rho. V is the volume of the body which need to float. So the volume of water which need to be displaced is less than V, because this is more than 1. So only a part of the body is going to emerge. Only a part of the body will emerge, and that will be enough for it to float, right? If rho is greater than rho L, then what? Then the volume of water which need to be displaced is more than V, and that will not happen. Then the volume of water which need to be displaced will be more than V, because in that case rho L by rho will be less than 1, and the volume of water which need to be displaced is more than V. In that case this body is going to sink, and if rho is rho L, then this is going to be 1, and the volume of water which need to be displaced is equal to V. In that case the body will look like this. In that case the body will look like this. So that's the case of just float. That's the case of just float. We say the body is just floating. Here it is floating happily, and if rho is more than rho L, then body will sink. Then body is going to sink. So that's the principle of flotation, right? So Archimedes principle gives you an idea when the body is going to float and when the body is going to sink. That will depend on the density. Alright, so that's about Archimedes principle. But the things are going to change if you go in non-inertial frame, if your observer lies in non-inertial frame. So if your observer lies in inertial frame, the buoyant force is equal to weight of the water displaced. Okay, thank you very much.